Yo, today I got a pretty easy problem for you guys. 2475, number of unequal triplets in an array. Um, this is classified as an easy, and the easy solution is definitely pretty approachable. It's essentially just brute force. But there is also a far more efficient solution, which is a little bit more convoluted, and I just wanted to take the opportunity to kind of articulate that approach if you had some sort of confusion. Okay, so quickly, let's just go through this problem description. It's pretty simple. So you're given a zero indexed array of positive integer nums. Find the number of triplets, I, j, k, that meet the following conditions. Okay, I is less than j, less than k. That constraint just exists so that you don't, count the same pair twice, right? So it's a combination, not a permutation, right? The order of which you select items doesn't matter, only the fact that you select those items. So there's no difference between choosing 3, 4, and 5 versus 4, 3, then 5, right? So that's just what this constraint means. And then the second constraint is that they're pairwise distinct, right? So none of the numbers are the same. So the first number and the second number are different. The first number and the third number are different. And the second number and the third number are different. Okay, return the number of triplets that meet this condition. Okay, so the simple, very simple brute force solution is just to look at each triplet and then check this condition, or I guess these conditions, and then add it to your number of solutions, right? So look at each triplet, look at each number, check that, I, j, and k, you can build this in when you do the check, doesn't really matter. And then just check, literally if this doesn't equal this, and this doesn't equal this, and this doesn't equal this, add that to your solution. So I'm pretty sure that that's what most people did, and that's fine, right? Because that's an n cubed algorithm, but since num's length is less than equal to 100, right, that's 100 cubed. So, you're adding 3 additional zeros, so that's not a big deal. It's definitely within the realm of what's possible to compute pretty easily. But what is the n-time algorithm? Well, the n-time algorithm for this problem kind of requires a strong statistics background, right? Or just combinations, kind of mathematics, which I guess for some people I've been seeing in the discussion is elementary school math. Wasn't for me, but again, I went to school in the U.S., so our education isn't really that great in the prior to college. And honestly, the college probably isn't that great either, but unless you go to one of the elite. So, whatever. That's a discussion for a different day. But the idea is, well, if you have numbers like this, so let's look at this example before I start getting all political about education in this country. If you have nums equals 4, 4, 2, 4, 3, for example, how would you find a combination of all numbers? Right? Well, a combination of all numbers. How would you find how many size 3 triplets, right? So how many triplets can you select from this system, right? Well, the idea there is n choose 3, right? So that's a mathematical concept, which is saying this is the number away from n things, where n is the length of nums, right? This is the number of ways that you can select 3 things, right? So there's n choose 3 ways of doing that. And where does that come from? Well, the idea is how many things can you select for the first thing? For the first number, well, there's n numbers that I can select from. And how many things can I select for the second thing? I have n minus 1. And how many things can I select for the third thing? I have n minus 2 things, right? But we can't have it where we can't overcount, right? Because selecting 4, 2, and 3, right, is the same as selecting 2, 4, and 3, because the order doesn't matter, right? And that's essentially what this system means here, right? So we don't want to overcount by saying that these two things are different. So we need to divide out the number of ways that we can count the same thing and being in multiple positions. So how many ways can something be in multiple positions? Well, when something's here, it could also be here, right? It could also be in this position. So there are how many ways? Right? There's 3 ways for something to be here. Times 2 times 1 equals 6. So there's 6 such ways that something could be overcounted. Right? For any digit, it could be overcounted 6 different ways because it could be in this position or this position or this position. Right? So the general formula for n choose k is n factorial over n minus k factorial times k factorial. Right, now I'm just kind of saying hand wavily that this is what the solution is, but if we looked at n choose 3, so how many ways can we choose 3 things? Right, well, we have n factorial over n minus 3 factorial times 3 factorial, which equals n times n minus 1 times n minus 2 times n minus 3 factorial, right? Because I'm just splitting up the factorial, because remember, factorials basically mean, you know, n factorial is n times n minus 1 times n minus 2 times n minus 3, so on and so forth. And the reason why I'm doing that is so that I can cancel these 2 things out, and then 3 factorial is 3 times 2 times 1, which is 6. So this is times 6, which is the same thing as the system here, right? So if I wanted to find all triplets, the number of triplets in total, right, just the number of triplets that I can get meeting this first constraint, right, equals, sorry, the reason why my writing is so sloppy is because the location of the table relative to where I'm sitting. It's a weird way of saying that the table's either too low or too high. Is n times n minus 1 minus 2, all that divided by 6. Right? So that's the number of triplets. But we still need to figure out this idea of there being overcounting. So we don't want to, because this will give you all of them, right? So this will give you all of them here, but it will also account for the triplet 444, right? And this is obviously not something that we should include in our final solution, right? 444 is not a valid triplet in our answer because it doesn't meet this pairwise distinct constraint. So similarly how like here, you know, we counted things and then we figured out like, okay, there's stuff we need to remove out. We need to divide out stuff that's going to get overcounted. We're going to play a similar game here. And what we're going to do here is we're going to say, well, what needs to get counted out? Well, we have the total number of triplets, but we need to subtract out number of triplets where where 3 items are the same. Okay, let's do this in another way. Another way of thinking this is that the total number of triplets, when you solve these kind of problems, and I know this from discrete math, sometimes you want to think about like, how can you break something big into smaller pieces to find out what you need to filter out, right? Because what we have is the total number of triplets, which is the total number in our array, right? N is the length of the array. N times n minus 1 times n minus 2 divided by 6. But we want to filter out certain triplets, right? We don't want to count all of them. We only want to count like a subset of the number of triplets. So let's think about the number of triplets in terms of other things and see if we can use that information to remove triplets that we don't need, right? So another way of saying this is that the number of triplets is what? Well, the number of triplets has 3 slots, right? There's 3 slots. So either they're all unique, right? So there's X, Y, and Z. So equals all pairwise unique And that's another way of saying there's 3 unique values. So there's a number with 3 unique values, right? And then there's cases where there's only 2 unique values, x, x, y. So this is 2 unique values. And then there's the case where there's only 1 unique value. And this is just another way of saying, like, all of the triplets can be broken into 3 cases. There's 3 unique values, like 4, 2, 1. There's 2 unique values, like 4, 4, and 1. And there's 1 unique value, 4, 4, 4. Now, we don't want to consider these cases, right? Because our answer is this system here. We want the 3 unique value system, right? That's what we want. That's our pairwise distinct, right? So we have the total number of triplets that we can get, which is this. And we want the 3 unique values. So the 3 unique values equals this minus the 2 unique values minus the 1 unique value. Right, so our answer, which is 3 unique values, so then I'm just going to move things over. So 3 unique values equals the number of triplets, and I'm just doing algebra here, or arithmetic. The number of triplets minus this information here. You know, my face is in the way, so let me just subtract it out. Minus the number of 2 unique values minus the number of 1 unique values. Okay? So we already know how to find this, right? Because that's just this formula here. Right? This number of triplets is this formula here. So we need to just think if we can find a formula for 2 unique values and 1 unique value. Okay? So how many, I think this one's a little bit simpler, right? So how many 1 unique value systems are there going to be? Well, if you look at each value, right? How many so for this system, let's look at the example again. So there's example equals 4, 4, 4, 4, 2, 4, 3, right? How many ways can there be a triplet where there's only 1 unique value? Well, let's first think about how many times each value happens, right? So there's 4 and it happens 3 times. There's a 2 and it happens 1 time, and there's a 3 and it happens 1 time. So this is like my little ledger, right? Probably going to be using a counter kind of hash table system to account for how many times each value exists. So 4 occurs 3 times, 2 occurs 1 time, 3 occurs 1 time. Well, how many ways can you get a triplet where they're all the same? Well, in order for all of them to be the same, I'm going to need at least 3 of the same value to populate, right? So since I have 3 4s, there's only going to be 1 triplet, right? Where it's 4, 4, 4. Right? That's the only way this is going to happen. And since it's ordered already, right, it's not like I'm going to be overcounting, right? There's just 1 triplet or there's 3 4s. Okay? And if we had, imagine this example was just a bit different. And it was 4, 4. So now the value of this was 4. So there's 4 4s. What would that mean? So let's color these 4s because it's a little confusing like this. So there's this black 4, this blue 4, this red 4, and this yellow 4. Well, how many ways could you choose 1 unique value where there's triplets, right? Well, now we're playing this game again of selecting, right? Well, I have 4 things that I can select, and I want to see how many ways I can select. I have 4 fours, right? So there's 4 fours. How many ways can I select 3 of them? Because that will mean that's the number of ways where I'm selecting only one unique value. Well, that's the same thing as saying what we've already said before. How many ways can I do 4 select 3? Well, that's already this formula over here. Right? We've already done the math and looked at, okay, how many ways can you select 3 things from something? Right? Because that's the number of times that we're going to be selecting a 4, and it's a unique value with just 4. Does that make sense? So the number of ways one unique values, right, is just the sum. We'll look at the count of each value. So for each unique value v in our system, we'll just say for that unique value, how many times is it in the system, the count of that value? How many ways can we choose 3 of them? Because that'll be the number that we need to remove from the system, right? Because we want to remove, because inside of our system, what we're going to get, so 4 choose 3 is what? Well, that's, oh, don't let me do basic math here. 4 times, I'm looking at this, so 4 times 3 times 2, so 4 times 3 is 12, times 2 is 24, divided by 6 is 4. So there's 4 ways, right? So let's write those out here. So there's 4 ways of choosing all 4s. You might be like, okay, why are you just writing 4s over and over again? Remember, because these are different 4s that I'm referencing. So there's this blue 4. So maybe this is the first one. And then this is the next one. And then this is the 4th one. Okay, which one am I? What is one I'm forgetting still? So black, blue, and red. Black, red, and yellow. Blue, red, and yellow. Did I mess that up? So 4 times 3 is 12. Times 2 is 24. Divided by 6 is 4. Which one am I forgetting here? Because 4 choose 3 should be 4. Or did I mess something else up? What is 4 choose 3? It's 4. Okay, so what am I... Somebody's yelling at me for being so stupid. Which one am I forgetting? Black, blue, yellow. Did I do that one? Black, blue, red. Oh, no, I didn't do that one. Okay, so I forgot. I didn't do this systematically, and that's why I messed up. Okay. So these are all the unique 4 pairs, right? So what I should have done is said, okay, black, blue, yellow, black, blue, yellow, black, blue, red, black, blue, red, blue, red, yellow, blue, red, yellow, black, red, yellow, black, red, yellow. So bang, bang. Okay. So this is all the pairs of 4 unique things that we need to remove from the system, right? So basically what we do is imagine we had a count of all of the, we had all the values that are in the system, which is the number of triplets. What we're going to do is subtract out these ones for 4, right? Because that's what this system will give us here. So we want to remove these ones. So we say, okay, We'll subtract out this one, this one, and this one, and this one. So we just basically subtract out the ones that we're over counting, right? Which is the count to the value, select how many ways can we select 3, right? So for 4, there's 4 4s. So there's 4 ways in which we can remove those 4s. And it's kind of unfortunate that I'm using the value 4 because it's like the value's 4, the count is 4, the number that you get is 4. So 4 4 4 is I'm saying a lot of stuff here. But you should do that for each value, right? Because imagine that there were also 3 3s, right? So that would mean that there would be an additional 3 3 3 in the system. So we also need to address for that. Right, so we need to look at the number of 3s and subtract that out. So we look at each unique value in our system and we say, okay, how many times does it occur? And let's remove the cases where it occurs in a triplet, and that's the count of 3, right? So to update what we've done so far, the number of 3 unique values, which is what we're looking for, equals the number of triplets, which is n times n minus 1 times n minus 2 divided by 6, right? Plus the number of 2 unique values, which we haven't determined yet, plus the sum of the value, but then we'll play the same game. So we'll call this C, count of the value. We'll call this count of V. We'll say X equals count of V. So X equals the count of the value. And then we do X times X minus 1 times X minus 2 divided by 6. So the last thing we need to do is just find 2 unique values, right? So how many ways can a value be counted twice in a system? So it's the same thing as looking at each value, right? For each value, how many ways can this value be counted twice? Well, let's think about it. So if you choose 3 values, how many ways can this value be counted twice? So you could have the value x, x, y like this. You could have x, y, x like this. You could have y, x, x like this. Right? So there's 3 ways in which this value, the same value, can be in the same spot, right? Where y is any other value in the system, right? So the number of values that doesn't equal x is n minus the number of values that do equal x. So the number of count of the value, right? And then you can have the value in one spot, the number of times it occurs, oops. And then the value in an additional spot, another time that it occurs. But you don't want to overcount these, right? Because you could have the value here and then the value here. But that means that you're going to be double counting it, right? Because like you only want to count it for the x in this position. You don't care when it's in this position. But this will account for both. So you want to divide by 2. Okay, and if that's a little hand wavy, I guess the idea is, you know, for this example, right? For the example 4, 4, 2, 4, 3. So if 4's in 2 places, right? That means that there's another value for any pair, right? There's another value that could be in the other slot. Well, how many other values could be in the other slot? Well, that's the number of values that don't equal 4. So, right, so there's 1, 2, 3, 4, 5. So there's 5 minus the count of 4 is 3. So there's only 2 other things that could be in the spot. So that's where this comes from. All right? And then the idea is, well, how many times could this occur? Well, how many times could there be a 4? Well, there's 3 4s, right? And then that means in the other spot, there could be any of the other 2 4s. But I just overcounted, right? Because this 4 is different from this 4. So if you have 4 and then 4, where this is a black 4 and this is a red 4 or whatever, you can't have it swap, so you want to divide that by 2. So that's the kind of hand wavy way. So that means that's what this is, right? So we can replace this with the sum of this system for each value. So our final solution is the number of 3 unique values equals n times n times n minus 1 times n minus 2 divided by 6 plus our new solution, which is we look at each sum, we call x equals the count of the value for each unique value. And we do n minus x times x minus 1 divided by 2 plus same thing here, x equals xcv x minus 1, x minus 2 divided by 6. And then you'll notice that these are the same sums here. Right, so what we can do is further simplify this. And just write out the whole system here. Right, so what's the runtime of this? Well, we have to determine the counts of each values, right? So that's going to take linear time. This whole loop is going to be also linear time because you have to look at each value and do a calculation. Right, so this is also linear time. And then doing this right here is just a constant operation. After you find the length is catched. So this is O of 1 time. So in total, it's just an O and N algorithm, right? We do O of N time to find the counts of everything, and then we do O of N time to find the sum. And then we do O of 1 operation. So I just realized I made a little mistake here. Right, because if this is the total number of triplets, I'm such an idiot sometimes, right? We want to subtract out all the things that we overcounted. Right, so this is a minus here. Right, we want to subtract out everything that we overcounted. So we can just use a simple Python script to make this happen. So with that said, let's just get right into it. Okay. Also, the new Leetcode interface is terrible. It's not terrible, it's just new, and like most things, you're averse to change. But I'm not a big fan of it. I never had a problem with how it was before. So that's my 2 cents about it. So we'll have this count of values called C, right? And we'll make that a default dict. And then we'll just get the count of each value. So we'll look at each num in nums. And we'll say, okay, the count of that num, I called it V before, so we'll just call it V. C of V plus equal 1. So now we have the count of everything. And then we're going to return what? Well, we'll return the total number of triplets. So let's set n to be equal to the length of nums. So the total number of triplets is n times n minus 1 times n minus 2 divided by 6. And then we want to subtract out the things that we're overcounting. Right? So we'll look at each value. We'll look at its value. We don't really care about the value, just the number of times that unique value occurs. So we'll call that x. So the first thing we'll do is this n minus x, x minus 1, x thing. So that's n minus x times x minus 1 divided by 2 plus, what was the other thing? It was the number of ways that the same item could be all three items at the same value. I'm sorry, I'm like having crazy brain fog today. Right, this system here, which is the number of times in a triplet all values are the same. So we have the value x, choose 3 of the same value, which is this, divided by 6. And then we want to look at we want to look at the we want to look at each value in C dot values. Now the problem is some of these values, they only occur once, right? And we don't want to consider the number of times that they occur in the system this way, because it's going to give us a weird negative answer, right? Because like the number of times a value that only occurs once occurs in a triplet, it doesn't happen at all, right? Because the value has to occur at least with frequency 3 in order for it to be the same value in an entire triplet. So in order to ensure we don't have situations where we're like overcounting things that don't exist, we'll just set this to 0 so that in those cases this gets set to 0. We want to do a sum here, and that should get us where we need to be. So let's try that. So int object is not callable. I always do that for some reason. So remember, we're multiplying here. This is going to think that I'm trying to call a function or something on an integer, but I'm not. I'm just trying to multiply. All right. So let's go ahead and so this was a very mathematically heavy problem, right? To get to the n times solution. Whoa, beats 97%. But we don't really need to worry about that too much, right? Because for this problem, honestly, the n cubed solution is fine. It shows that you have an understanding of just how to apply a brute force solution to make something work. But to know that there's some statistical kind of base mathematics behind this problem to determine the n times solution is pretty cool. Okay, guys, so that's all I got for you today. I'm looking marvelous today, I must say. Peace out.